Thanks a lot. So this is my work in measuring attention, and this is work that I did at Cornell. I'm a PhD student, and in collaboration with Chartbeat. So I love shoulder surfing. I think probably lots of you do too. And what's great about it is there's a lot you can understand about users by the way that they scroll through pages, what they pause on, what they attend to, what they skip over. And I'd love to be able to capture this attention and this distribution of attention across the screen. But I want to be able to do it at a large scale with millions of users. So what tools are there to do this, and how would I approach this? Well, a current understanding of user engagement online is mostly limited to the document level. These are metrics like bounce rate, page views, and time on page. And these are helpful for understanding attention at a very high level, but they're less helpful for understanding fine-grained user attention. And this is the kind of attention I'm interested in. So this is the goal of the work. The goal of the work is to design and validate a method of measuring this sub-document user attention, this very fine-grained HTML element level attention on the page. So here's our approach. First, we're going to develop a model, and this is a model of sub-document attention that exploits and uses prior research on attention and small-scale lab studies and builds on these studies and helps us to inform our knowledge of attention online. And second, we're going to validate this model. I would love to make sure that this model works on large amounts of data, many users. And so being able to validate on many users and validate on large data sets of real-world users is important. And so this is exactly what we do with a large data set of reading users. And we use a metric that we know about users to validate, and this is cross-language reading rate. And I'll talk about this in a moment. But first, let's talk about attention. How do people measure it now? Most of the time, if we want to measure attention on a document, we use eye tracking. And this is exactly the kind of fine-grained attention that I'm interested in measuring. But it doesn't scale. It doesn't scale to people across the web, millions of users, and so it's not useful for these kinds of contexts. So what do? What is our approach to fix this? We need to measure attention, but we need to measure attention using what we have, standard browser data. How do we do this? Here's sort of a very simple example of a model that uses standard browser information, and this is using a metric I talked about before, time on page. We take the time on page, the amount of time a user spends looking at a web page and measured in minutes or seconds, and we distribute it uniformly across the page. And so each element on the page receives a chunk of the total attention proportional to the size of the element. Really simple model. Does it work? It has a bit of a problem, which is that it doesn't take into account viewport information, what is on the user's screen. So for instance, if the user only scrolls down to the image and doesn't see anything beyond that, we don't measure that in this model, and this is bad. We want to be able to take into account what the user sees and how the user interacts with elements that they see. So we need to, very first thing we need to think about is incorporating the viewport in measuring attention. But what else can we learn about the viewport? And what can we learn about attention on the viewport? And so this is where we can turn to measuring attention in lab studies, and it's sort of specifically eye tracking. And if you look at eye tracking in context of users looking across web documents, scrolling, reading, looking at search results, you see that actually that attention across the viewport is fairly predictable. And it follows sort of a normal distribution across the page. This is great. We can use this. And we can use this in conjunction with this idea that the viewport is important and measuring attention in the viewport is important. So let's modify our model. And instead of looking at attention across the page, look at attention just on the viewport, and look at attention according to this attention distribution that we know from eye tracking. And so as the user scrolls across the page, we can second to second measure the attention on every element in seconds or minutes using this distribution. And we call this the Gaussian viewport attention model. I like this model. It's empirically motivated. It builds on prior research, but does it work? That's kind of the important question. Can we generalize from this eye tracking data and generalize from these small-scale lab studies to many users, millions of users? How do we validate it? So I talked very briefly about this data set we're using. It's a data set of 1.2 million users. It's collected on a popular news site with our collaborator Chartbeat. And we can apply this model to sessions in our data set. And we can understand for every user, for every session, for every element, how much that user is attending to that element. But we can do a little bit more. For the text elements, we know how many words are in each paragraph. So if we know how long a user spends on each paragraph and we know how many words there are, we can compute a reading rate for every paragraph. Why is this important? We know how fast people read. We know how fast people read in English, certainly, but also in many other languages. In fact, there are 9 languages of readers in this data set, and so we can compare the reading rates in aggregate for each of these languages as measured by the attention model, and we can compare them to what we know from reading rate studies and how people actually read and what rates they read at. So I want to be clear, this is a validation approach, and this is how we can verify that the model works and measures attention, because reading rate is a byproduct of how we measure attention in this model. But we aren't really specifically interested in reading rate, although as a sort of an aside, this I think is the largest reading rate study ever conducted, as sort of like just in our validation section. So how does this work, and do these models work? Let's talk about first the uniform attention model. On the x-axis, we have the empirical reading rate. These are measured by reading rate studies. On the y-axis, the estimated reading rate, as approximated by the model using our measurement of attention. And now here's the uniform attention model. This is the one that has, I think, a couple flaws in how it measures attention. So how well does it perform? If it performs well, all the languages should be along the diagonal. If it doesn't, maybe there's some noise, I'll accept some noise, but if it doesn't, they won't be. And then we'll know, it's not a very good measurement of attention if it certainly can't measure reading rate. So how well does it work? Not very well. Empirically, we know that English readers read at around 220 words per minute. The model estimates English readers as reading around 600 words per minute. This is very bad. Let's see if we can fix this with what we've done with attention and our Gaussian viewport attention model. How well does the Gaussian viewport attention model understand attention in a way that we can calculate reading rate? So if we zoom in on this part here so we can see the errors a little bit better, you can see that the Gaussian viewport attention model is much more accurate. It's much more accurate across all languages. English especially, now we know it's about 220 words per minute empirically. In this case, it's measured at almost exactly 220 words per minute. So we know from this that the Gaussian viewport attention model is a much, much better model of attention and much more accurately measures attention across the page. How can we use this? Well, we can apply this to images. So we use the same data set, and we look at different topics of articles in this image, in the data set, and we say, well, which articles and which topics have the most engaging images? And we can apply the model, and we see that, yes, actually, there are some things that are expected. For instance, sex articles provide very highly engaging images compared to, say, articles about politics. And so do music articles, interestingly. So this is the kind of information that as an editor of a website or a writer, you might want to know about your articles, you might want to know about your audience, and this is the kind of information that subdocument attention can provide. So here are a couple more implications and applications of the research. One of them that I'm most interested in is understanding language. Could we use this attention distribution across the page as measured by this attention model to better summarize the page and include elements in the summary that matter to readers? We can also understand engagement better. Can we identify and aid struggling readers? Readers maybe with disabilities who can't read the page as well and maybe require some sort of adjustment to the layout, or maybe readers who don't understand the content of the text and require a little bit of contextual cues. And of course, we can understand user preferences as well. And sort of in a recommendation context, if we know more about how users interact with documents and what they care about, we can provide them better suggestions. So to conclude, we can reliably measure subdocument attention without the browser, within the browser, and without eye tracking. And this is especially useful in contexts where eye tracking cannot scale, which is in context with millions of users or lots of people in a data set. So thank you very much. If you're interested in the models, and there's a third model I didn't cover, you can read the paper. Thanks.
Thank you, Max. Is everyone setting it up already? Question here? my neighboring University of